This is the big one. See, Python's syntax is so easy, so friendly, that it can give you this dangerous false sense of security. But look, in a real interview, when you're under pressure, they don't just want to see code that works. That's the bare minimum. They need to know that you understand why it works, especially when things go wrong.
So the very first hurdle is all about the fundamentals. It's about the execution model. Basically, how does Python actually take your script and run it? This has nothing to do with fancy syntax. It's about the machine's point of view. And this is where most candidates fall down, right at the beginning.
Okay, so picture it. You're in the hot seat, and the interviewer slides this little snippet of code across the table. Just take a look. How would you answer this? Why does calling this function over and over again just keep adding to the very same list? Your answer to this one little question says everything about how you think about the language.
Now this is where it gets really interesting. The weak answer, because lists are mutable, well, it's not wrong, but it completely misses the point. The interviewer isn't testing if you know what a list is. They're looking for that strong answer, the one that shows you get that the function object itself and that default argument a equals a array are created only once, when the function is first defined, not every time it's called. That's the signal they're looking for. So to turn up the heat a little, a good interviewer might poke at this old myth that Python isn't a compiled language. But guess what? It totally is. Before a single line of your code actually runs, it's compiled down into something called bytecode. This is the low-level language that the Python interpreter actually understands. And they're not just going to take your word for it. A really strong candidate can prove it. They can pop open the dis module and actually show you the bytecode instructions. They can explain that deep down in CPython, there's this giant loop in a file called ceval.c that just chugs through these instructions one by one. And that extra layer, that interpretation step, is precisely why Python is slower than a natively compiled language like C.
Okay, so if you've made it past that first filter, we move on to the next one. The focus now shifts to how Python represents all of its data in memory. This is all about the integrity of the language's most fundamental building blocks.
And here's the next little test. Seems super simple, right? Is versus equal sign. But let me tell you, treating them like they're the same thing is a massive red flag for any senior role. Why? Because it immediately shows you don't have a solid mental model for how Python deals with objects versus their values.
So here's the crucial difference. Is checks for object identity. It's basically asking, are these two variables literally pointing to the exact same object in memory? It's like checking their ID card, their memory address. Equals, on the other hand, checks for value. It calls the _EQ_ method to ask, do these two things have the same content? Confusing them is bad, but what's worse is trying to explain it by talking about weird implementation details, like how Python caches small integers. That's a dead giveaway of shallow knowledge.
Now let's talk about the dictionary, right? The absolute workhorse of Python. The question seems simple enough, but it cuts right to the heart of how hash tables actually function. So why the super strict rule? Why do dictionary keys have to be immutable?
And this is a perfect example of knowing a rule versus understanding the reason for the rule. A weak answer just goes in a circle. They have to be immutable because they need to be hashable. Okay, but why? A strong answer explains the consequences. A dictionary uses a key's hash to figure out where to store the value. If you could change the key after you put it in, its hash would change and the dictionary would be totally lost. It would never be able to find that value again. The data would just be gone.
You know, a good interviewer will keep digging on dictionaries. A lot of textbooks will tell you that when two keys have the same hash, Python uses linked lists to handle it. That's how some languages do it, but it's not how modern Python works. A candidate who has actually been in the trenches wrestling with performance knows it uses a more complex technique called open addressing to find the next empty spot. That's the difference between academic theory and real-world knowledge.
All right, let's move on to filter number 3. And this one is huge. This is what separates people who can write a quick script from people who can build a stable, long-running system. It is all about memory and when objects live and when they die. So the big question is, how does Python clean up its own mess? When your program is creating millions and millions of objects, what's the system that decides, okay, this one's done, we can free up that memory now? Your answer here really shows if you've ever had to hunt down a memory leak.
The basic answer you hear a lot is reference counting. And look, it's not wrong, it's just not the whole story. Every object keeps a little counter of how many things are pointing to it. When that counter hits 0, poof, the object is gone. But a senior engineer knows that this system has one massive blind spot.
The strong answer always includes the backup plan, a generational garbage collector that's designed to solve the one problem reference counting can't handle.
So what's that fatal flaw? It's something called a cyclic reference. Just imagine a list that, inside of itself, contains a reference pointing back to itself. Well, think about it. Its reference count will never ever hit 0, even if nothing else in your program can see it anymore. That is a classic memory leak. And that's exactly why Python needs this other system, the garbage collector, to periodically pause everything, hunt down these tangled up cycles, and clean them out. Knowing this isn't trivia. It's absolutely essential for building anything reliable.
Okay, on to our final and honestly most advanced filter. This is where we get into real senior level thinking. At this point, the interview completely changes. It's not about right or wrong answers anymore. It's all about your judgment, your reasoning, and your ability to defend the decisions you make. This is so important. Look, anyone can write code that works. A senior engineer can tell you why they wrote it that way and what the trade-offs were. They can justify performance choices, memory strategies, and security concerns. The why is literally everything. So what does that actually look like? Well, you don't just use NumPy, you justify it. You argue for vectorization because you know it pushes the heavy lifting down to optimize C code, avoiding the slow Python interpreter loop. You don't just read a huge file, you explain why you're using a generator to process it line by line to keep from blowing up the system's memory. And you absolutely, under no circumstances, use eval on user input. And you can explain exactly why it's a security nightmare. That's what engineering maturity sounds like.
So after all of that, after all these filters, how does the hiring manager actually make the final call? Well, it usually comes down to a few key red flags. Telltale signs that reveal a lack of that deep fundamental understanding.
Yep. There are 3 big ones that interviewers are looking out for. And honestly, spotting just one of these can be a total deal breaker no matter how good your other answers were.
First up, the tutorial signal. This is when you can recite the textbook definition of garbage collection, but you've got no story about a time you actually had to hunt down a memory leak on a real project. Second, the anti-tooling bias. This is when someone dismisses standard professional tools like virtual environments or linters as useless overhead. It's a huge sign they haven't worked on a serious team. And finally, the logic gap. That's when your clear, structured explanation just dissolves into wild guesses the second the problem gets a little more complex. And really, at the end of the day, it all comes down to this. Passing these filters isn't about memorizing tricks. It's about showing you have a deep, intuitive feel for the machine. We don't hire people who just write Python. We hire people who know where a value lives, when it's created, and why the interpreter behaves the way it does, because that is the only knowledge that truly matters.